So I told you number 3 was a trick question because it didn't really, like, this concept of finding end behavior model didn't really apply. But let me show you why it's a trick question rather than just you taking my word for it. All right. So I'm going to plot the graph of y equals sine of x. All right, good looking graph. You know, Desmos does a wonderful job when it comes to creating nice curved graphs, giving you a sense of scale and all that. So it's really nice. What this is saying is, again, you never want to lose sight of what a limit question is asking you to do, regardless of how it's asking you to do it. It's asking us to determine what y value is the graph or the function approaching as x increases to infinity. All right. So we're supposed to do this analytically, but we don't have any kind of basis to understand how one would do this analytically. All right. What we can do is take a look at the picture and see if it even exists to begin with. All right. So I'm just going to go out to infinity. It's going to be a while. It doesn't seem to be leveling off on any particular value. It doesn't seem to be settling in on a number. If you want to get out to infinity faster, you can zoom out a lot, scroll over, slide it over. Not anywhere near infinity. It's crazy. So you zoom out a lot, like a ton. And then once you're satisfied that you've gone far enough, you zoom back in and you say, oh, you know what? It's crazy. It looks exactly the same as it did for the small values of x. All right. So what happens is the sine function, y equals sine of x, oscillates between 0 and 1 from negative infinity to infinity. All right. It never settles in on a particular value. You can keep going, but just when you think you've gotten to infinity, and let's say this is like you think we're at infinity right here. Somebody else will say, well, no, I went further and I'm not at the one that you thought it was. I'm at this 0.157, 148, whatever. And then somebody else will be like, oh, I can go even further. And now I'm at -1. All right. Or I can go even further. Now I'm at -0.98. And then you keep going and going and going and going and going. And you never settle in on a finite answer. That's because there is no finite limit for a sine function. So we would say that this limit does not exist. Right. Now, in terms of analytically determining that limit, well, that's the thing. It kind of goes back to what I was saying a couple of classes ago about continuity. In order to understand continuity, we need to understand limits. But in order to understand limits, we need to understand continuity. Right. So it's a chicken and the egg kind of thing. All right. So what we get is like a basic working definition of continuity, talk about limits, and then come back and talk more about continuity now that we have a formal understanding of limits. All right. This is the same idea. I can tell you why analytically the limit doesn't exist, but you need to know about derivatives first. So what we'll do is we'll just take it on faith for now that the limit doesn't exist. And then when we learn some about derivatives, we'll come back and talk about why this limit does not exist. All right? There's actually a few cases like that. But looking at number 4, now we're back to something that fits with the end behavior model approach. So we take the term with the highest power top and bottom, and divide them. So for the EBM, it'd be y equals x over x squared, which would simplify to 1 over x, right? So instead of finding the limit of this, we'll find the limit as x approaches infinity of a simpler function that we know behaves the exact same way as the original function for large values of x. And again, this isn't a proof, it's just a demonstration and justification. But if I give you the original function y equals fraction x plus 1 over x squared plus 3. So we got this looking function here. It's a pretty decent looking function anyway. Y equals, 1 over x. They behave much, much differently from one another. All right. They don't resemble each other at all for small values of x. But for large values of x, you see that they're now in lockstep. They're behaving exactly the same way, to the point where they're almost indistinguishable from one another. And for large values of x, they will be indistinguishable. All right, you really have to zoom in substantially in order to show any kind of difference between these two functions. But if you were ever to actually get out to infinity, they would have the same value, the same y value. All right, so what we would do is we would substitute in the infinity for x here. And we'd say, okay, well, what is 1 over infinity? All right, 1 over something that is infinitely large, or 1 over a number that keeps getting larger and larger, is going to result in a value that gets smaller and smaller, approaching 0. So that's what our limit's going to be. But I can show you a quick justification for that one, because it's kind of a strange one, but it's also the basis of what we're going to cover from moving forward. So we don't want to gloss over that. But if this limit is equal to 0, then so is this one. All right, but let me kick over to Desmos and show you real quick. All right, I'll turn these off. Go back to standard zoom. So let's say I have some function 1 over, I'll call it a. Well, not a function, but an expression. All right. That 1 over a has a numerical value of 1 when a is equal to 1. All right. I'm only going to focus on positive, so I'll change my low bound here. I'm going to make this pretty big. Oh, I don't know where that decimal came from. And I'm only going to go by 1. All right. So I'm going to just slide my slider over to the right. Now, I can tell you that if I make a 2, then the result is going to be 1/2 of what we started with. All right, because 1 over 1 is 1, 1 over 2 is 1/2, 1 over 3 is 1/3. It's getting smaller and smaller, but I want to show you that it's getting smaller and smaller, but also approaching the value of 0. All right, so 1 over 120,000, very tiny decimal. 1 over 330,000, even smaller. 1 over 540,000, getting even smaller. 1 over 740,000, getting smaller, getting smaller, getting smaller. If you go even further, you'd see that right now you've got to be pretty convinced that it's approaching 0. There's never an instance where it went through 0 and it started becoming negative. Right, but if you need to really convince yourself, just keep adding zeros as much as Desmos will let you. It's when it kicks over into scientific notation that I tend to lose people. I mean, that's assuming I had you on board to begin with, but what I tend to do is I take this number and I say, okay, let's take that and put all the zeros in front of it, because that's telling us to move the decimal place 11 units to the left. This is the same as saying 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, then 1, 0, 6, 3, 8, so on. All right. It's a number that's definitely approaching 0 as you increase the denominator. All right. So what we're saying here is that, because you can never actually divide something by infinity, but what you can do is you can get into the theoretical aspect of it and say, if I could divide it by infinity, what would the result be? Because remember, we don't actually have to get there. It's what we're aiming for, right? The trend is taking us towards zero. That's all we're looking for, is where is the trend taking us to, all right? The next one, we have a 3x, that's the high power on the top, of x to the fourth high power on the bottom, so our end behavior model. Y equals 3x over x to the fourth, simplifies to y equals 3 over x cubed. All right, let me get rid of some of this fluff here. All right, so I could take my original function and actually I'll just take it from scratch here. Y equals fraction 3x on the bottom, x to the fourth, 2x squared, oops, Rocky, plus in there, 2x squared plus 1. All right, similar looking graph to the previous one. Now, the end behavior model, we're going to find the limit of that as x approaches infinity, 3 over x cubed, or quality 3. Let me make that look a little nicer. All right, so y equals 3 over x cubed. All right, again, they look wildly different from one another in the short run, but in the long run, as we go out to infinity, same deal. They're in lockstep with one another. Specifically, they seem to be approaching the x-axis, which has a y value of 0. All right, that's graphically. All right, now, analytically, we'd write 3 over infinity cubed. All right. Well, infinity cubed is another form of infinity. So we have a constant divided by infinity. Right. So what I can do here is like I did before, just as an illustration, I can take 3 over a cubed create a slider, and you'll see that the value is decreasing in size. If I change the parameters of my slider, I'll only make it go out to 1,000 this time by ones. As I increase the a value, see that it's another situation where it's approaching 0. All right, it's just going to approach 0 quicker. All right, that's the difference between this problem and the previous one. They'll both approach 0. The rate at which they approach 0 will be different, but they're both approaching 0. And so that's our limit. All right. So that's a little bit more on the infinite stuff. Right now, the next page we get into, or we keep going with the constant. I can tell you that if you're talking about like a multiple choice question on a test, and it just says find the limit, I'll have no idea which method you're using. So use whatever you want. If you want to do it by graphing or analytically, go for it. Right? In fact, for a multiple choice question, I'm not going to tell you to do it any particular way. I just want the answer. All right. But if I ask you to do it analytically, you got to show me the end behavior model stuff. Now, what you can do is kind of work to the middle, meaning you get the answer from the calculator, you start doing it analytically until you get stuck. But then once you go to the calculator, you realize what the answer is supposed to be. You can kind of start working your work toward that answer. That's perfectly fine. All right, that's just being industrious. All right. But for the analytic cases, sometimes it's as simple as just popping in the number. I just found that as a student, I was following the steps, following the procedure, getting stuff right, doing a good job, but never really understanding why things worked the way they did. because I was just focused on getting stuff right, and that's fine too. So, like if you can kind of start, like we want to get stuff right on the test, I understand. But if you can at least make the attempt to try to understand why things work the way they do, then things get a lot easier. All right. Here's a typo for somebody. They should say analytically. All right. So why, in this case, are we able to just put the number in the expression, get the answer, where in number 6, we put the number in the expression and we got this mess, right? There was a significant difference between the type of function that we were working with here and the type of function that we're working with here. All right, let me just show that to you really quickly. And it goes back to something that we were talking about before we started getting into limits. All right, something that seemed like sort of a throwaway topic where you're like, all right, here's just another thing to study, I guess. But if I put in y equals 2x minus 1, what we're looking at here is a linear function. All right, linear functions are always continuous. We say everywhere continuous. All right, what that means is that there's never an instance in which there'll be a break in the graph, like an asymptote or a hole or anything like that. All right, so let's take a look at this other function that we created, y equals fraction, parentheses, x plus 2 squared plus 4. Minus 4 over x. All right, now you look at that and you say, oh, look, another linear function. This is great. All right. And actually, if you're really thinking about it, you realize that that's actually not great. I'm just trying to move this so I have a little space to write. The issue that we run into there is that it's not a linear function. It just appears to be. It's still a rational function because there's variable top and bottom of a fraction. It's in the form of p of x over q of x, all right? Function of x over function of x, all right? This is not a linear function. It's a rational function. And specifically, it had a point discontinuity. All right. It's a rational function with a point discontinuity. You say, well, how do you know? Well, I don't. No, I know because we did the problem, right? But if you scroll along, you get to 0, you see that there's an undefined, right? At 0, 4. I'll just plot that. All right. So it's a rational function with a point discontinuity, but it has all the hallmarks of a linear function except for that hole. That hole just changes its category. All right. It's not that anymore. It's not a linear function. All right. But there is a discontinuity. So we kind of start wondering, wait, is that it? Is that the thing? Because if there's a discontinuity, will that then mean that I have to do some kind of algebra to solve? Well, it's also a case where maybe you have a vertical asymptote, right? So I'll show you another one. So let's say you have, I need a note here. We'll say a rational function with a vertical asymptote. I'll just say, I was going to just say asymptote because I was being lazy, but I'm going to write vertical asymptote. All right, so I'll say y equals, let's go with x, oh, let me get a fraction in here, x plus 1 over x squared minus 4. All right, now the graph's pretty busy looking, so I'm going to turn off some of the other stuff. All right, so this one has some asymptotes. Now, if I look at this at the asymptotes, x equals 2, x equals negative 2. Oh, I wish it would let me just copy. Come on, for crying out loud. Oh, there we go. If I look at it at just the asymptotes, you know, the limit as x approaches negative 2, the limit as x approaches positive 2. I'm going to get d and e in both cases. All right. So we start recognizing that the type of function is going to dictate what happens with the limit. All right. So if a function is everywhere continuous, the limit will exist at the y value corresponding with the given x value of that function. All right, that's a mouthful. But what it's saying is we have this equation y equals 2x squared. This function is continuous. It's everywhere continuous. So the limit will be whatever y of negative 2 is. All right. All you have to do is figure out the y value that corresponds with the given x. All right. So just means that we pop in a negative 2 and we get an 8, and that's it. Whereas in number 6, we had a whole, we had to evaluate, we had to simplify, all right, in order to be able to come up with a solution. Same thing's going to happen in not number 5, I don't think, but number 7. So let's actually jump to number 7, because this one is not everywhere continuous. So this is not continuous for all x. There is a discontinuity at x equals 1. Now that x equals 1 happens to be the point that we're looking for. All right. So that's an important distinction, because if we have a discontinuity at x equals 1, but the question's asking about x equals 5, then we go back to what we just did here and it'll work. You plug it in, you get a finite answer, and that's the end of it. All right. But because there is a consistency between the discontinuity and the limiting constant, that tells me that we're not going to get a finite answer without doing some extra work. All right. So what we would do, I mean, you could try, but if I were to plug in the ones, 1 squared minus 1 over 1 minus 1, that's going to give me 0 over 0. And just like we learned with number 6, that's indeterminate. Indeterminate means that there's an answer. You just got to go looking for it now. All right. Fortunately, this isn't the world's worst problem in terms of simplifying algebraically. The top is factorable. Specifically, it's factorable in such a way that there's a common factor that cancels. All right. And so what we would have here is the indeterminate situation, which has a hole in the graph, can now be filled in by the simplified form through direct substitution. All right, so 1 plus 1 would give you a 2, and that would be your limit. And specifically, you just got to be clear about this. that's the limit of the original function, even though it's the limit of the new function, the simplified one. That's not what the question was asking us. It was asking us what's the limit of the original function. So our final answer would be this rather than just saying this. All right. But let me just show you really quickly. I'm going to save all this stuff and post it on Blackboard. It's kind of like a nice little running tab of note taking and all that good stuff. But this next piece, I'm just going to show you real quick. So you have y equals x squared. I got to put the fraction in. Right key. X squared minus a 1 over x minus 1. All right. Now, there's a hole in this graph at the x value of 1. Right there. It says undefined. All right. I'll accentuate it by plotting 1, 2. All right. Now, if I plot my simplified function, y equals x plus 1, you see that it fills the hole. All right. So if we evaluate the y equals x plus 1 for when x is equal to 1, analytically, right? Graphically, we would never need to do this because you just look at it and say, okay, well, what's the location of the hole? Well, I plotted it as 1, 2, so my money's on it being 1, 2, right? But analytically, it's telling us that we have license to simplify and use the limit of the simpler function to help us determine the limit of the original function, right? Oh, I wanted to check something real quick. I don't know what was happening with that. But anyway, so going back to number 5, it really is just a matter of assessing continuity. So what we can do is we can look at that original function and see if there's any funny business. All right. So taking a look at this, I can tell you that we have the function y equals x squared plus 2x plus 4 over x plus 2. All right. That has a discontinuity at x equals -2, specifically a vertical asymptote. And again, just a reminder, you get that by taking your denominator, setting it equal to 0, and solving for the value of x. All right. So in this case, we got a vertical asymptote discontinuity at x equals -2. It's continuous everywhere else. I mean, you can put the notation down if you want, but that's kind of beyond what I'm looking for. All right. More so, it's telling me that I can now make a determination of what the limit is simply by direct substitution. I can take this 2, plug it in for all the x's, and it's going to spit out a finite answer. 2 times 2. And I won't have to do any algebraic manipulation. All right. And that's really important. It might not seem to be very important at first. You look at it and say, oh, it's not a big deal. What do I care about that for, But the bottom line is knowing when you need to factor and when you don't, that's pretty important. All right. So four plus 4 plus 4 is 12 over 4 gives you a result of 3. So we get our answer straight away. What happens is, and it happens all the time, it's actually pretty terrible. People will factor because they think that's what they're supposed to do. Something looks like it's factorable, so I guess I got to factor it. And it's like, you know what? You kind of missed the point there. That's not what we want to be doing. All right. So keep your eye on the prize. So the last one on this page, again, we want to make a determination of whether it behooves us. Sorry, I'm multitasking here. I realized I never put the word of the day link on our class. I put it on a class that I did not tell that we were doing the word of the day, and because of that, I've got to imagine there's going to be some head scratching going on. But I just put the link there. It's on the left-hand side of the pane, and so just a reminder: the word of the day is an opportunity for bonus credit. Okay, so I'll give a word of the day, and all you have to do is click on that link on the left side on Blackboard. It's right above, or it's right below where you clicked in for online meetings. And you just click on that, and a nice little survey comes up, picture of a can, my name. My son drew it, it's really funny. You put your last name, your first name, what the word of the day is, and use the word of the day in a sentence. Right. So later on in a couple minutes, maybe 10, 15 minutes, maybe 5 minutes, maybe 30 seconds, I don't know. I'll announce what the word of the day is, and you just put it in that link. All right. So what I'm going to do is factor the bottom here just to get an idea of what the asymptotes, if they are in existence, what they are and how they may be relevant. All right. So we have x plus 3 and x minus 2. So we have discontinuities at x equals -3 and x equals a +2. All right, very important because one of them is a removable. We have a common factor here. Because one of them is removable, that makes it a whole. The one that's not a whole would be the vertical asymptote. All right. So we have an agreement between the limiting constant and the hole in the graph. All right. If we had an agreement between the limiting constant and the vertical asymptote, we might be thinking that the limit doesn't exist. It could be infinity, it could be a DNE. But because it's an agreement between the whole and the limiting constant, that means that we can simplify this thing and we'll get a limit as a result. Right? We're just looking at what y value would fill in the hole. All right. So we have a common factor that cancels out. So I would find the limit as x approaches 2 of 1 over x plus 3, and then resubstitute there. 1 over 2 plus 3 gives a result of 1/5. And so that would be my limit. Remember, the point doesn't have to exist there. It just has to be the destination as you're coming in from the left and right. But we're trying to do this without actually coming in from the left and the right. All right. So I gave an example of a rational function with a vertical asymptote. So this is actually a good example of a rational function with a vertical asymptote and a hole. All right. So we would have y equals fraction x minus 2, x squared plus x minus 6. And we have the whole at 2, 1/5. I'll make this look a lot nicer later on, but for now, I'm just kind of just getting it down. Right? And the vertical asymptote x equals -3. Right? Let me save it before I forget, because that's a big bugaboo there. All right, so this is limits and discontinuities. You know what? I'll say continuity. Because there is one case where it's continuous. All right, and I'll get this up on Blackboard for you later. All right, but there was that one that's kind of staring at us. That limit as x approaches 0 of the sine of 3x over 2x. All right. For that one, I'm actually so it really doesn't fit in this page, but I didn't want to get into like a whole page or like a whole lesson involving trig limits. So what I figured was I just dump this on this page and we would just talk about it separately. But I can tell you that there's a rule, and rules are terrible when it comes to math because rules usually have no explanation. Yeah, but this is one of those rules where you're going to take it on faith for now, but later on you're going to say, oh, okay, that's why it worked. And that moment will be after we talk about derivatives. All right, we have to get to something called L'Hopital's rule in order to understand why this one is going to work the way it does. But I'll say that the rule is that the limit, I don't need a capital. I don't know why I'm going capital all of a sudden. Limit as x approaches some value a of the sine of a over a is equal to 1. All right, so that's a rule. There's other trig rules, but this is the most popular and therefore, for our purposes, the most useful. All right. I'm sorry, why did I say a? I meant 0. Oh, Schlemmingus. Nobody knows. Just got in the habit of writing 8. So let me show you what this looks like on Desmos. So this is a trig case. I'll come up with a better title for it later. Kind of a placeholder for now. All right. So let me turn off this. I'm going to make folders. I'm going to make it all like a little, more user friendly. Because I plan on working on this while I watch the Giants game. I'm a big Giants fan, like huge Giants fan. I kind of love them. Like I have one son. My other son is the Giants. So I just put it that way. I like the Mets. I'm a big Mets fan, but the Giants are like part of my life. Like if the Giants didn't exist, the New York Giants, not football, not baseball. If the Giants were taken away from me, it would be like I was losing a limb. And then people feel that way about their teams. Like if you're a big sports fan, I know that American football isn't popular worldwide. I know soccer is the most popular, or football, is the most popular sport on the planet. But anybody who's a sports fan has their team. Like that. That's how I feel about mine. That being said, I don't think it's going to be a good year. So I feel like I'm going to get a lot of work done during the Giants game tonight once they're getting the crap kicked out of them after the first quarter. Right. Oh yeah, Mets. Well, the Mets let me down this year, so that's an issue there. So anyway, this trig case, I can write it as y equals. I mean, I could try to use like an a, but I'm just going to use an x. And I'll show you why in a sec. Let me get a fraction in there. So we would say the sine of x over x. All right. Now I can tell you, I'll bring it in because we're approaching 0 here. As I get closer and closer to 0, you see that there's a hole there. All right. It's undefined. Okay. So then I say, well, why, or if I were a student, I'd be saying, well, what's the big deal here? Well, you have an x here, but you have a's there. All right. What we would say is a is some function of x. All right. So what that tells me is I can make this 5a if I want. I'm sorry, not 5a, 5x. I could replace a with a 5x. All right. I can replace A with a 0.5x. Now, it's kind of hard to see because it's happening so quickly, but in every case, no matter what I change these values to, at 0, it's always going to be hitting, I mean, it's undefined. In this case, indeterminate, I can get it to lock on, but it's always hitting that value of 1. All right, so what I can do here is I can actually make this an A, call it capital A. And Desmos will understand that, which is great, but I could also allow for A to be some function of X. You know, let A equal 2X. Oh, well, actually, it would have been nice. For some reason, Desmos didn't understand that. This way. Still wants a slider. All right, well, I had a good thing going there. It understood it for A, but it didn't like it when I put it with other stuff going on. But like I said, you can put whatever you want in there for A and it'll work out. All right, it'll give you a limit equal to 1 at that location. Right, but it does have a hole there. Right, so that's an important consideration. Now, how does it help us solve the problem? Because these two things aren't the same. What we're going to do is we're going to make them the same. All right, what I want to have happen here is I want this 2 to become a 3. It would be really nice if that were a 3. It would be great if we 1. Done. Yay. The problem is I can't just change a 2 into the 3. Right, but what I can do is multiply this by 1/2, top and bottom. And what that'll do, you know, so the equation is still balanced in the sense that if I'm multiplying top and bottom by 1/2, I'm essentially multiplying the whole thing by 1. I'm not changing the value, right? But it's going to allow me to cancel this 2 here. So then I can write the limit as x approaches 0 of 1/2 sine of 3x over x. So then I would be saying, okay, well, I want a 3x. I have an x. So now what I'll do is multiply the whole thing, top and bottom, by 3. So then that'll give me the limit as x approaches 0 of 3 over 2 sine 3x over 3x. So then I'm only like one tiny step away. A constant doesn't have to be contained within the limit. There's actually a bunch of limit properties that we kind of gloss over, but I'm going to just kind of jot them off on the side here. And it really just boils down to the idea that you can do a lot of things with limits that transcend ordinary algebra, right? So if I have something, for example, so these are some rules of limits. If I have the limit as x approaches some constant c of a of x over b of x, that would be the same as saying the limit as x approaches c of a of x over the limit as x approaches c of b of x. All right, so we can break up division. So that would be one rule. Another rule, get my indeterminate stuff out of here. Would involve multiplication. So the limit as x approaches c of a of x times b of x. That's going to be the product of the two limits. just have to shrink it down a little bit. Right, the same would hold true for addition and subtraction. All right, so I'm going to snag this, copy. I'm going to put a plus or minus in between. All right, so there are rules that hold true in each of those cases, but there's another one last one that involves a constant, right? I'm going to get a little lines of demarcation here. So the last one is actually one of the simpler ones and the one that applies here, but I wanted to make sure you had all these rules too. And it's all going to be saved, as you know. But you get purple for those keeping score at home. You could have the limit as x approaches c of some constant k multiplied by a function we'll call a of x. That's going to be equal to k multiplied by the limit of a of x. All right. So there's some rules of limits, but there's a couple of them that sort of transcend what you would normally expect to be the case algebraically. All right. And it does take a lot of getting used to. And unfortunately, this is the thing that I always hated about the structure of these courses, calculus, even algebra and all that stuff. After this unit, you may not see this again until like the end of Calc 3. You know, it doesn't come up very often, these rules. Yeah. But when they do, they're really important, critically important, right? So in this case, what it's telling me to do, or telling me that I can do, is factor out the 3/2. So after all that, at long last, I am now justified in saying, okay, this can come out to the front. All right. And the reason that's beneficial is because this follows the form of this rule that we just created and you took on faith. All right. So this whole thing is equal to a 1. And so the whole limit is actually equal to 3/2. All right. Now, like I said before, on a test, if it's a multiple choice question, I just need the answer. So you just put it in your calculator and call it a day. The issue is, you know, like that level of understanding that you want to have going into the next course. All right. So that's where things tend to kind of fall apart for some people, where it's like, yeah, I really need to understand this. And then there's other people that it's like, I just need to get it right. You know, so it's really like, where do you fall in this whole thing? Right. But yeah, that's the concept of a limit. The next page, we're only gonna spend like 5 minutes on it. By the way, the word of the day is limit. What we're gonna do is talk about what's called the slope of the secant line, right? And then once we do that, next class, we're gonna incorporate the concept of a limit to that, and that's where we're gonna get to a derivative. All right. So we're slowly but surely getting to this concept of a limit. I'm sorry, of a derivative. But we're, you know, you may not like it, but we're taking our time getting there, just so we get the deep understanding of all the pre-calc stuff that will help in terms of truly being, you know, a master at this concept. All right.